Yeah. There we go. To operate. So last time, so let's talk real quick a little bit about something we did last time. Compatible numbers was like one of the only things we did out of section 4.1 yet. My God, whoa, trying to get you high. Compatible numbers, if I had 48 plus, what do you got, Jeff? 26 plus 12. Are there compatible numbers in there to start with?
48 and 12.
Yeah, 48 and 12, right? And that makes 60. Woohoo! All right, so that's compatible numbers. So that's, I said last time, bless you, it's impossible to make a complete list of compatible numbers because they're just numbers that go together well, right? That's all there is about compatible numbers. So let's talk about that new thing we just saw today called compensation. So if I had to do 43 plus 36 plus 19. Do you see compatible numbers up there? No. Right, I don't see any numbers that kind of make a whole number, right? So compensation means taking some from one and putting it on the other one somehow, right? So what do you wish this was? So that it would have acted more like these did. What do you wish this was? 37. So if I make it 37, this has to become 18, right? So technically what I'm doing, if you really want to see all the parts, I'm just going to rewrite this like this, right? This is the part you wouldn't have to show yourself, but it's still a true statement. Still, I didn't change anything, correct? That's just another way to say 36, right? Mm-hmm. So therefore, 19 minus 1, 18. So if I take 1 from the 19 and put it on this guy, I get here. So you don't need this middle step, but I just want to kind of show you more details. And now you got compatible. Now you've created compatible numbers. So of course this would be 80 and 18, 98. And I'm using associativity and all that kind of shit, right? Mm-hmm. Okay. How are we all doing? So compensation is a beautiful word for it because it's exactly taking some from one and giving it to the other one. That's compensation. Blah, 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 blah. So, not surprisingly, this is an example of additive compensation. Holy macaroni. Right? So what about, oh, yeah, there's something in the middle here that's interesting. So we'll say this is additive compensation. I'm trying to keep this organized for you. Compensation. There's an example of additive compensation. Then there's something called the equal additions method. All right, so for example, if I had to do this, 47 minus 29. It's a little gross, yes? So instead of, let's see, earlier we talked about like changing that one, sort of like the 123 took 23 away. Can't I instead add something equal to both? So obviously, two things are an equal distance apart, and they'll stay the same distance if they both move the same amount in the same direction. Does that makes physical sense? Mm-hmm. So what do you wish this number was? 30. So then you have to bump this up to, no, you got to bump it up, right? So if you subtract more, to keep the answer the same, you have to start with more, right? Yeah. So however far apart these two numbers are, These two numbers are the same distance apart.
Mhm.
So they have the same answer, yes?
Yeah.
So 29, 47, if I move, and they are a certain distance apart, and this distance would be the answer. Yes, that distance would be the answer. So if I put him up to 30, I have to put him up to 48, so the distance is the same. Same answer. I like it. Did you guys ever use any of these, just doing it, or no? Yeah, you guys ever know that you're allowed to do this? No? Does it make sense?
I think like in day-to-day stuff and like mental math, and that's pretty much.
Yeah,
the
yeah.
stuff we're
This
looking
is,
for.
well, you know, I teach math, so
Yeah.
this is constantly what I'm doing. Students, I'll do math on the board and I'll get the right answer. They're all like, oh my God. I'm like, I'm just doing this kind of shit. I just know all these stupid little things and I'm like, bam, 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 bam. The answer is this. Right? That's it. There's nothing amazing. I just do it all the time. But, you know, you got to do this kind of thing. You do. In real life, you do this kind of thing. It's good to know these little tricks. And call me enough to get 18 is crazy. So you see why it's called the equal additions method is because, of course, I'm adding an equal amount to both things. How we doing? But just to kind of compare this to when I was adding two things, if one goes up, the other one has to go down. Yes? Because so here's one way I like to look at it. If I have 4 people in this room and 5 people in this room, there's 9 total people. If one person walks from this room to the other room, now there's 3 here and there's 6 there, and there's still, of course, 9 people. So to keep an addition the same, the numbers have to go up and down by the same amount. Does that make sense? Where subtraction is more of a distance idea. In fact, that's what subtraction was primarily initially used for, was to see how far apart things were. And maybe, possibly. Okay. Then, of course, kind of makes sense. We have what's called multiplicative compensation. And this is something like, what do you got, Jeff? Let's say 52 times 5. Don't you wish this was a 10? Well, this can be a 10 if it had another factor of 2. So you steal a factor of 2 from this guy.
So 26 times 10.
Yeah. So half of 52 is 26. Twice 5 is 10. Do you guys see that? And again, behind the scenes, all I'm doing isn't 52, isn't that 26 times 2? And isn't that 26 times 10 then? Bam. So I kind of steal a factor of 2 from him and put it on him. Isn't it still a factor of 2 in the problem somewhere? Isn't it still in there? It doesn't matter if it's on the 26 or if it's on the 5. It just has to be on one of them, so it's in the answer. I don't know if this is making sense. Okay. And of course, this is much easier. Just got to throw a 0 in.
So then could you do it 13 times 20? It'd be the same answer. So if you're.
Yeah, you can keep going if you wanted to, sure. Yeah. Still the same idea, 13 times 20.
Still the same
Yeah.
answer.
I do that kind of thing all the damn time. All the time. Okay. So that's compensation. It doesn't really, this one feels a little less like compensation, but it's kind of thrown in because it's sort of the same vein of what we're trying to do. But it's just the equal additions method. But then you have additive compensation, multiplicative compensation. You take from one and you give to the other one. Okay, maybe. Okay, I like it. Not too bad. In the video we saw reference to something called left to right method, and I talked a little bit about it. So, I don't know, something like 580 plus 133. So the left to right method, you do it the opposite of what we're used to. Start with the hundreds and move on. So if you add the hundreds, what do you get?
600.
So you got 600. Then you add the 80 and the 30, 110. And the 0 and the 3 is 3. Holy shit. And then you get
713.
713. Crazy. And again, you can see inherent in there is a lot of discussion you could then have later about where carrying stuff comes from. Okay, nothing too crazy. I like it. Yeah, they got a whole thing about multiplying by powers of 10. That should not be anything we should spend too much time on, yes? If I multiply something by some power of 10, all right, let's see. Let me throw a little something more. So it's 11 times 1,000.
11,000.
Holy crap. But let me just get a little preview, because that's pretty straightforward, yes? Not much could be said about that. What about 2,300 times 10,000? There's a beautiful way to do this. Say again?
230,000?
Let's see. 2, 3. 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0. 0, 0, 0, 0. You guys, you just collect the zeros? Yes?
Mhm.
Maybe?
Yeah.
10 times 10 is 100, 2 zeros, because there's 1 0 and 1 0, right? That's a beautiful thing about powers of 10, or like round numbers. You just do the first part, and then you collect the zeros at the end. So what is this? Let's see. Pop. Pop. 23 million. Crazy sauce. So that's a beautiful example of, you can't look at it and get to tell. You put the zeros and then you go, oh, that's what it is, right? Okay. What about if I had to do this? I'm not going to tell you what this is called. What would you do there if you have to do it in your head, and what trick do you think you could use here? What's the best thing to multiply 25 by besides 1? 4, right? Because what's it make? 100. And then we're back to the powers of 10 thing, right?
Yeah.
Does this have a 4 in it?
Yep.
Ah, so you can do compensation. Right? So what is 36? It's
12 times 4.
9 times 4. So then I'll get 9 times 4 times 25. Right? 900. Crazy sauce. So this would be a question I could say, I have 36 quarters, how much money do I have, right?
Mhm.
And 900 cents. Yay. Because every 4 quarters makes $1, right?
Yeah.
That's what this is really doing. Every 4 quarters makes $1, so I have 9 sets of 4 quarters. Okay, I like it.
What is that? Is just compensation but multiplicative?
Yeah.
This is called special factors, which I don't really like that title, but oh well. We deal with it.
Not too
4 times 25 is a special set of factors because they make a nice 100. Right? But what is it really? It was compensation, but in a certain direction, right? It's compensation, but with a little extra focus. But still just compensation, to be honest. Okay. Now, so none of that should have been too crazy, but there is quite a few different things, yes? We got to try to keep them all straight, what they reference. Now, as a student, for your students, it's not gonna be so important they remember the names of these things. What's gonna be important is, can you do it whenever it's the best idea, right? Okay. So the first part of this section is mental mathematics, getting the exact right answer. The second part of this section is estimation. What do you guys know about estimation already? Does anyone have, let's see, I'm gonna make this one, anything you wanna say about estimation? Is there any specific situation or general thing you think when I say estimation? Yes?
Like rounding up?
Rounding up, I love it. So estimation could involve some rounding, makes sense.
It's
Right.
a guess?
Guess,
Yeah.
but not like a totally random guess, right?
Yeah, no.
What's 40 minus 13? Pineapple, right? But yeah, I know what you, yeah, okay. So let's talk about, well, I could do, yeah, we'll do it out of order. Why not? Let's talk about rounding first. First off, what the shit does rounding mean? What's our standard rounding methodology, right? How would you round 47 to the nearest tens? Yeah,
So, if it's closer.
yeah.
to-
So anything from 45 up would go to 50. Anything 44 down to 40 would go to 40, correct?
So 45, the 5 is considered to go up?
Yes.
Doesn't have to be like.
So
over there?
0, 1, 2, 3, 4
Mhm.
goes to 40. 5, 6, 7, 8, 9 goes to 50, so it's perfectly balanced.
Okay.
I like it. How's everybody doing? Now, when would that be bad? So like, if I wanted to use rounding to estimate 45 plus 55, what would 45 get rounded to? 50. And what would 55 get rounded to?
60.
And what do you know is kind of wrong about that answer? Is it too big or too small?
Too big.
We know for sure it's too big.
Mhm.
So the problem with just rounding our standard way is if I have a number of 5s in my problem, the answer is going to be bigger than it's supposed to be for sure, right? You guys with me? And we want an estimation method where the answer is close to the actual answer. Blah, blah, blah. So there is a weird thing. So this one I'm going to call, this is our standard rounding. Then we have this interesting thing called rounding to the nearest even. So if I had 45 plus 55, what's the nearest whole number to 45? Nearest even whole number.
46.
I don't want to say this. Well, yeah. Let me think. No. So, all right. Wait. Nearest even tens is what I'm trying to say. That's what I'm trying to say. So, like 40, right? 4 is an even 10. Okay. Nearest even 10 for 55. 60. So the hope with this is, if there's a bunch of 5s, there should be some evens, some odds, but still, that's kind of hopeful. I don't know if you understood when I first said this. I don't like this method much. As I was writing it down, I was like, and there's a method, it's called this, but it's out there. And to be honest, isn't that the right answer in this specific example, right? Okay. Blah, 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 blah. Now, here's a little bit better idea. Round to compatible numbers. So this is rounding with more of a focus, not straight up traditional rounding, but just rounding whichever way gets me to compatible numbers. So for example, if I had 24 times 42. So it's not even, let's see, it's not quite rounding, really, but we still call it. So if I round this, well, let's see, what would this number would be best if it was 40, right? In fact, that's what we rounded to 40. But what would be great for this number to be? 25, because that would go with the 4. They're compatible then. So if we make this 25 and then make that 40, this will be an approximation, certainly not the right answer, yes? 25 times 4 is 100, so 25 times 40 is 1,000, 11. Now what is 24 times 42? Can somebody do that?
Thousand
1,008. So we got pretty damn close. Here's our approximation, right? Approximation symbol. Approximately 1,000, and the actual answer is 1,008. Pretty close. So the best method up there so far is the rounding to compatible numbers, because you can be kind of smart about it. Notice one thing that happened here. This number went down, this number went up. In a multiplication problem, that would keep the balance better, right? I'm not going to make too big of an estimate or too small of an estimate, and they kind of tend to average each other out. Does that make sense?
Yeah.
So I can be smart about my estimation method by not blindly rounding, but keeping in mind, like for multiplication, if one goes up, the other one's got to go down. Same thing with addition. Okay, maybe. Okay, so this is interesting. I kind of like that we started with rounding, because rounding does show up in some of the other stuff. And by the way, of course, rounding gets even more interesting when you start bringing decimals into play. Yes, everybody's favorite. That's in our future. Some beautiful decimals, and before that, some beautiful, beautiful fractions. All right. So here we have something called range estimation. Now this one is more true to life, to be really honest. If I had to do 375 plus 4, doesn't really matter, does it, Jeff? Not really. 242. All right, 375 plus 242. Give me like a crazy low estimate. What would you do to get a low estimate for this?
600.
No. So the way to get the low estimate is just to force them both down. 300 plus 200.
Okay.
11. So what would be the high estimate?
7.
Yeah, this would go up to 400. This would go up to 300. 700. Of course, I would say do one more thing and just average those, right? But I mean, that's the high-low range estimate. What does the book call it? I forget. Oh, true. That's it. It's called front-end estimation. Now, let me make this a little more specific. I'm really sorry. I'm not really being very nice with your notes, but too bad. Why would this be called front-end estimation? What's the front end of this number?
300.
3. Isn't that exactly what kind of told me? Go down to 3, go up to 4, right? Front end estimation means ignore the details. Just look at the biggest place. Just look at the beginning.
Ugh.
What's up? We all right?
Yeah, I was gonna sneeze.
I understand. This section is kind of dense with quick little things. I really want this word, this phrase to make sense. Why is this called front-end estimation? Because I'm just looking at the front. I don't care about the rest of it. Okay. It gets even better. Hold on. What about a multiplication problem using front-end range estimation? So something like, what do you got, Jeff? 217 times 89. What's the low estimate? What would you do?
200 times 80.
200 times 80. And of course, 2 times 8 is 16. 1, 2, 3 zeros. Yeah? And then what's the high estimate?
300 times 90.
300 times 9. 3 times 9, 27. 0, 0, 0. So somewhere between 16 and 27,000. I have a big range. And that's why if I was doing this, I would kind of average the two, right? Let me stop for a minute. Okay. All right, now comes, oh, shit. Just buckle in. If you really liked this, okay. Okay. Now we get the 1, 2 column front end. Oh boy. I've lost my I don't know what I'm using for, anyway. 1 column, 2 column. Front end, yeah. Okay, oh my God, okay, we're gonna be okay. We're gonna be okay. I was listening to a comedian a while back, and every now and then he would say, we're having a good time. We're having a good time. So we're gonna be okay. One column is kind of dumb, I'll just tell you right now. One column is like low end estimation. So what the shit does this mean? So one column would be like 769 plus 342. So all one column is, it's the low end of, oh gosh, you guys are gonna love this shit. It's just the low front end estimate of what the hell. So all this means is you simply look, we put a little estimate, 700 plus 300, it's 1,000. So it gets more interesting with the 2 column. That would be 760 plus 340, and that's kind of nice because those are, so this becomes that, so this is approximately this. It's not another example, Jeff, it's just 2 column. So 760 plus 340, so 1 column is the first number, 2 columns is the first 2 numbers. That's all that really means, right? So what's 760 plus 340? 1100, I like it. Okay, nothing. The most important point here is every method has its advantages, disadvantages. But what is your overall thing you're trying to do is make the answer as close to what the real answer is, right? So obviously the more detail you bring in, the closer you are to the real answer. So on one level, this is kind of dumb. Because you still have stuff to deal with, right? And the whole idea of rounding and estimating is supposed to make the problem as easy to do in your head. But it's closer to the right answer for sure, yes? Okay. Blah, 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 blah. Oh, and then we have, okay. Then we have the ultimate thing. This sounds like a trip to the auto shop. Front end with adjustment. Okay. So front end with adjustment. What have I been drinking so much? Does exactly what it sounds like. So here's, what does front end mean? What would the front end by itself give me for this answer? Yeah, so the front end would give me 700 plus 300 is 1,000, right? So front end would give me 1,000. The adjustment would say, all right, 69 and 42 is about 100 or so, right? So it's a little more subjective. So it's like front end, you add those two numbers, and then you throw in kind of a quick little estimate of what the rest of it is. Okay. All that's relatively unsatisfying for me, but they're all valid methods that are out there. Okay, crazy sauce. Man, this is an exciting day, I know. Now, let me say how I personally do estimation, right? None of this is how I personally do estimation. I've already shown you one thing I do. If I had to estimate, uh, 48 times, what do you got, Jeff? 107. If I had to estimate this, I would take one up and take the other one down. Right? So which one am I going to take up? Obviously.
48 to 50?
Yeah, so I'll be 50 times 100. So as long as you take one up and one down, the product should remain relatively close, right? And that's easy. Now, real quick, what is 48 times 107? Can somebody do that?
5,136.
Not bad, right? It's pretty good. That's good for government work. I like it. What do you think I would do if I was dividing stuff? So like, 200 and 11 divided by, what you got? Chuck, you can do it, buddy. 43. Sure. And I want to estimate this. Now think about this for a second. Think really hard about this. Think really hard. You ready? What's 10 divided by 2? What is it?
5.
Holy crap. And what is 10 divided by 5? 2. Now, so if I make the bottom bigger, the answer gets smaller, right? So if I want to change this so the answer is still 5, and I make the bottom, let's say I make the bottom 8. What's the top got to become to make the answer still 5? 40. It's got to become equally big, right?
Mhm.
So subtraction, what do I do when I subtract two things? Don't I have to change them by the same amount, same direction?
Yeah.
So division, I have to change them by the same kind of factor, the same direction, right? Or at least the same direction. So here, if I want to estimate division, so multiplication, up and down to balance out. Division, if I make that go down to 200, of course I will, because that's the closest whole number, right? I'm going to make that go down also. And what's 200 divided by 40? No.
5.
And so somebody, quick hands, McGee, what's 211 divided by 43? Or anybody?
Oh.
It's 211 divided by 43.
4.90.
4.90?
Heard you with something.
And then probably other stuff, yeah?
Yeah.
Okay. That's pretty damn close, right? You guys understand? To me, that's, when I teach estimation, that's the most important thing to teach, is the idea of balance. When I'm adding or multiplying, they have to up, down to keep the answer roughly close. Subtracting, dividing, they have to both go up or both go down. Are you guys semi with me?
Yeah.
Okay. Real quick question. Anybody ever been or is currently a waiter or a waitress?
No.
Yes, yes, yes? Okay. Do you ever experience people that claim they don't know math, so they're sorry if they leave a bad tip or something?
Yeah.
Yes? Or people that just leave bad tips and they, you know.
Yes.
Do you have a, back in the day, sorry?
Sorry.
That's okay.
I was talking to myself.
Oh, you're, Back in the day, they didn't have on the receipt, they didn't say at the bottom what your gratuity should be,
Uh-huh.
right? I think nowadays, most of them do that, don't they?
They have
Yep.
like,
Because, you know,
Some even calculate.
waiters
it
and
out
waitresses complained enough, they're like, what the shit, so they finally put that on there.
Yeah.
So people didn't have as big of a, I don't know, Matt, that's okay, we did it for you.
yeah,
Anyway,
couple options.
did you guys have ways to estimate what your tip should be based on the size of a order?
Well, the way that I would tell, you know, they're like, oh, what's normal? So I'd tell them like 20%, and then, you know, I'd be like $2 for every 10, you know?
There you go, yeah.
So then people would be like, oh, I have a $50 bill, $10? I'm like, that's 20%. And I was like, leave me 8.
There you go. I like it. So $2 for every 10, that's 20%. 2 out of 10, it's 20%, 11. Or if you're doing 15%, so how would you do like 15% of 89.13?
Oh, gosh.
Oh shit. First thing I do is make it 90, right?
Okay.
You guys with me?
Yeah.
So 15% of, this is all on the side, by the way, because we haven't officially talked about percentages. This is just me showing something real quick. What is 10% of 90? That should be,
No.
is everybody cool with that? 10% of something is 1/10 of it, yes? It's 1/10 of a full thing?
Yeah.
So that would be 9. If 10% of 90 is 9, what is 5% of 90?
4.5.
4.5. Right? Half of that. So then what's 15% of 90?
13.5.
13 and a half, yeah. So if you have a $90 bill, you're like, $90 cost or something, you're like, you better leave me at least freaking $13.50, right? Okay. I was never a waiter or waitress, but I had a friend who was, so, but she worked at a rib place, and I remember one time she opened a book, and all these 20s fell out, and she was like, oh, I forgot I put them in there to press them, and I'm like, and we were 16, 17, and I'm over here, I'm like, you forgot you put money in a book, you forgot. Anyway, sorry. So I was like, man, I should have probably become a waiter or waitress. Okay, so enough of that. Last thing I want to talk about is calculators. How many of you guys actually have a calculator like this one, like the little, how many of you guys have like a TI graphing calculator? There we go, TI graphing calculator. These little dudes are awesome. They do way too many things, you don't even know. This thing does about 215 to 300 functions. I can't remember when some functions I don't even know how to get to be honest. And they cost like $15. It's insane. Anyway, on your calculators, you should know how to do like parentheses. Let me see, do I want to get into this now? Maybe. No, screw it. We're done today. We're done. Next time we'll get into calculators. So bring your calculators with you next time for sure. Please, dear God, whose phone is that so I don't lose mine? Okay. Thank you. And that is enough for today. So I'll have the quiz graded next time. Yes?
When do you put grades into the actual, like, grade books?
Alright, man. Yeah.